Hello everyone and welcome to this webinar about Cloud HPC and in particular about meshing a pump or an impeller using snappyHexMesh and cfMesh. This is Ruggiero Poletto and I hope you can hear me fine at the moment. This webinar is gonna be part of a series of webinars held by Cloud HPC, and we're gonna talk about the new desktop app we have implemented and the new desktop app we can use and distribute in the coming day. This is the presentation we're gonna make today. So during the presentation, at any time, you can interact with me, myself, the presenter, and make questions using the chat. I try to keep an eye to the chat itself. So if you want to interact with me, feel free to type on any message. First, a brief presentation of the company. CFD FEA Service is a company founded in 2018 which is committed into cloud technologies and engineering applications in particular. Our main business area are software development, in particular as far as engineering applications are concerned. Cloud HPC, we are a provider of computing power in the cloud dedicated to engineers. And obviously, we are also dedicated to consulting and engineering design. Our headquarters is in Verona, in North Italy, but we operate basically all over the world in all the continents. What is Cloud HPC? Well, it's a computer cluster, so a huge amount of hardware resources where someone can perform engineering simulations such as CFD analysis or FEM analysis. The advantage of using remote hardware resources compared to in-house hardware resources is that you can have a high fidelity infrastructure which is maintained by a team dedicated to that IT infrastructure. So you can avoid downtimes, you can have software up to date with the best technologies at every time, and also the hardware technology keeps improving. All of this in basically a transparent way. So basically the user doesn't even realize what is happening under the hood. Every time you enter the Cloud HPC website, you always get the latest developments and the most advanced technologies we can provide. Thanks to Cloud HPC, you can speed up your simulation, that's for sure, because you can use way more hardware resources than those available on your computer. You can just focus on your product. You do not waste time anymore setting up PCs, installing software and stuff like that. Everything is made available for you on demand. And obviously you just pay the software and the hardware if you're using that. If you're not using, thanks to a SaaS methodology, you don't have any fixed cost of maintenance like having a person dedicated to the hardware maintenance and hardware updates at all times. And obviously the system setup is always ready. Okay, so you just have to register to the Cloud HPC and automatically you have all the system ready to go for your analysis. Today we're going to talk about CFD analysis and in particular of a software named OpenForm. This is an open source software developed by OpenCFD or the Open Foundation, depending a little bit on the branch you are using. And this software makes available quite 2 or 3 meshing algorithms which can be used in order to generate a mesh. It is a quite common open source tool, widely used both in academic world and as well as in the industry. and it's getting a sort of benchmark, at least in the open source software CFDs. In the open source CFD software, it is definitely a benchmark, and it represents a milestone against which any other software has to compare with. OpenFOAM gives you a meshing tool named snappyHexMesh. This is the default meshing tool available in OpenFOAM. It is an Oct3 meshing software. This means that it is based on polyhedral cells, and into the algorithm is based into splitting this polyhedral into smaller ones. Input files can be STL file, so someone has to generate STL file separately and submit these STL files to snappyHexMesh in order to produce the mesh. And there is also an output file, which is the OpenFOAM mesh file format. So currently it is not possible to generate mesh with Snappy to other CFD software, unless we produce, let's say, a custom mesh converter. And it is possible to use snappyHexMesh with MPI parallel analysis. So it is possible to use OpenMPI and multi-core approach in order to compute this mesh. snappyHexMesh is actually not the only meshing software available. If you are using the ASI version of OpenFOAM, you can also run cfMesh, or you can buy a license, or you can rent a license on Cloud HPC of cfMesh Plus, which is the commercial version of cfMesh, which includes also user interface, very comfortable and very convenient to use in order to set up your own case. Before getting into the details about the mesh and how you have to prepare the geometry in order to generate a mesh, it's worth a while understanding how the snappyHexMesh algorithm works. Okay, in general, the meshing is defined in 4 steps. The first one represented here, we have like the shape of a car, which represents the objects we want to mesh, and then we have an external rectangle, which is the fluid volume we want to mesh, and then you can see we have small little squares which somehow split the big square rectangle, the fluid volume, and this is the mesh as it is generated. Well, the first step of the snappyHexMesh algorithm is the base mesh generation. This is a structured block mesh, so it means that we divide our fluid volume into regular mesh generated by squares. Obviously, we can define how many the dimension of this square. This is the base mesh dimension, obviously. But the first step is very simple, and this goal is just to define this structure block mesh as drawn over here. The second mesh is called the castellation, and it allows the definition of a refinement of our mesh as the cells are intersecting our input geometry. So we can see the car geometry over here, and we can see that the big square of the initial block mesh are divided into smaller ones. Well, this is the castellation phase, and it is fundamental in this phase to define a refinement level. So how many times we want the big square to be divided into smaller and smaller meshes, cells, as we're getting intersected with our geometry. And then there are the cut cells. In fact, in this phase, the mesh still doesn't follow precisely the profile of our input geometry. For this, there is a snapping phase where we cut and we adapt the cell size to follow exactly the profile of our input geometry. In this case, it's the car geometry. And then there is the last phase, which is the layer extrusion. Here we can see just in this area over here. Well, this is an extrusion from the wall, also called inflation layer in other meshing software, and this allows to better represent the boundary layer, and it's very important in order to reconstruct the wall gradient of the velocity and consequently the wall shear stress and the wall force produced by the shear force produced by the skin friction, basically produced by the flow as it invests, as it surrounds our body. It is also important to define a fluid part, a fluid point, in particular one between phase 1 and phase 2 of our mesh. If you see, everything that is inside our car has been cancelled out, okay? But since the first mesh is generated inside and outside our geometry, we have to provide a fluid point from which snappyHexMesh is able to reconstruct which is fluid, what part of our mesh of our domain is fluid, and what instead is solid and has to be cancelled out before the simulation actually starts. As we said before, in order to generate the mesh, we had to provide Snappy with a certain number of STL files, which represents the geometry we want to produce. Well, in our case, I generated this impeller geometry, and we need to generate at least 5 or 6 files. These are the walls, represented here in gray or white, okay, translucent white, and they are basically all the solid walls of our domain. We have the impeller, which is the red part down here, and it's actually the rotating part of our domain, the rotating walls of our domain. We have inlet and outlet. Inlet is here at the top and outlet here at the bottom left of my picture. And these are two separate geometries, STL files, which are able to produce where we can define the flow rates or the outlet pressure. And then something else very important is another STL file which represents the rotating zone. In here is this yellow part of the domain. It's basically a sort of STL file which includes completely the impeller geometry, but differently from the impeller geometry, this is a closed STL, so it's an axial symmetric STL, which actually is generated to communicate snappyHexMesh what part of the domain is placed in rotation, okay? What part of the fluid domain is placed into the rotation. Differently, the impeller only specify what part of the walls are placed in rotation, okay? So this is a surface STL, this is a volume STL file, okay? So this is the difference between these two input files. As we said before, today we are presenting our software named BC Snappy, which is a software made available on Windows and which allows users to define easily all the parameters for snappyHexMesh to generate the mesh. It works on Windows, as we said before. It allows to generate a mesh with a very little amount of parameters. It's compatible with our cloud HPC.cloud service, so it is possible to generate the input files for the mesh and submit the mesh on cloud HPC. And at the same time, it is not just compatible with snappyHexMesh, but also with cfMesh and cfMesh Plus. Today we're going to see an example of how you can use this file, this executable. In a little bit I'm going to open it, and at the same time I want to do with you another part, which is the mesh calculation. In fact, in our website, at this link, which you can type right now, we made available a tool which allows easily to calculate the mesh dimensions on using snappyHexMesh. In particular, it allows us to understand how big a base mesh can be, how many surface layers we have to add, or alternatively, how many refinement levels we have to apply to a specific cell. Okay. Keep in mind that these data are fundamentals and they are strictly connected to the turbulence models you are going to use later in the CFD analysis. In particular, here I placed two examples. If you want to submit a simulation with K epsilon, well, you have to make sure that Y plus is in the range between 30 and 300. Or if you want to submit a simulation using K omega SST, well, you have to make sure that your simulation, hold on a second, I think I have to modify because I received informations that no one can hear me. Okay, I think now we are back in track. So I was saying that in here, with K epsilon, you have to make sure the Y plus, the wall refinement at the wall, is between 30 and 300, while for K omega SST, the wall refinement Y plus must be lower than 5. So depending on these parameters, you can obtain different level of wall refinement, and now we're going to see that in the calculator. So I'm going to go now into the calculator to show how that works. So this is the URL of the calculator, which can be, as we saw in the slides before. Well, you have to set the tip velocity of our impeller. In our case, we set the dynamic viscosity and the density. Here I just leave by default the air data, and they are going to be all right. The Y plus required, which is 30 level, so we want Y plus to be in the range for K epsilon, and the length, so the diameter in this case of our impeller, which is 0.6 meters. In here we can set the number of surface layers. We can set it to 8. The expansion ratio 1.2, that's okay. So let's set it 1.2 again. And final layer thickness 0.4, that's okay. We get information about the cell sizes, which allows us to define then the refinement level for, and we get in here the base mesh dimensions, which as you can see is 0.078 meters, so about 80 millimeters in our case. Well, we're going to use these informations in order to generate the mesh and to set up the mesh for our case. So I am now going to open the mesh mask, the Beachy Snappy tool we mentioned before. So the tool is quite simple. It consists of basically two separate parts. Okay, the first one, I have to upload the input files, the STL files I have over here. So I just go to the desktop, I just go where I prepared my input files, I just select all of them, and in a simple click I'm uploading all the input files. It is also possible to open Salome, so the preprocessors, the CAD preprocessor, which allows us also to view these STL files and which allows us to operate with them. So if we wait a second, I'm gonna open Salome and I'm gonna open again these input files in Salome. So I just open the STL files, I go to my desktop, and under files I have all the input STL files. So 1 second that all the files are gonna get open, and then I start again operating. So yeah, I can activate them, and here they are, all my input files. So I now go back to the interface and I go to the menu in here. Well, first of all, it's important to understand if we are working, what unit we are using. If you see the unit over here, they are millimeters. So we have 630 is the diameter of the impeller. Okay, so we have to make sure we convert everything back into meters. Okay, so we apply a scale factor of 0.001. As a coarse mesh, we said, using the tool I showed you before, that we have 8 centimeters, so 80 millimeters. So over here, I just apply in the unit of the drawings 80 as the base mesh, the coarse mesh dimensions. I have then these zones here at the bottom, and step by step we want to define all the input files in this case. So I just set Salome on the left hand side of my geometry. Well, and one by one I'm gonna import all the patches. So input, wall outlet, well, rotor, not really at the moment. Pressure outlet, we're gonna add inlet and impeller as well. Alright, so in here we imported all the STL files. I didn't import rotor just because rotor is a rotating zone. So in snappyHexMesh, this is not defined as a patch, so as a solid boundary, as a solid wall, but this is defined as a cell zone. So a part of our domain which is placed in rotation. So starting from here and having a look back at what we did here, we set 4 refinement levels and 8 layers. So for the impeller, we have to set refinement level to be 4. So using the tab, I can move on. And with number of layers to be 8. An impeller is a solid wall. Then similarly, we do a similar setup for all the other walls. So wall outlet, wall inlet. So sorry, I have to set it to 4 and 8 walls. Pressure outlet, we don't have to define sorry, any specific refinement, but we just turn the type into patch. Inlet, again, we don't have to specify any specific refinement, but we turn the type into patch again. So we just verify. Wall outlet is a wall, wall inlet is a wall, and we verify the refinement. Pressure outlet is a patch. Pressure inlet is a patch again, and impeller is a wall, and we have refined. For rotor, we just have to define the rotor zone. We can optionally define a refinement, but we can leave it as it is. Down here, we can set how many cores we want to use on Cloud HPC to submit this mesh, and what version of what type of meshing algorithm we want to use. So snappyHexMesh with OpenFOAM 10. If you are happy, we just press on Run on Cloud. We generate a new folder which contains this first version of the mesh to be generated. So test snappy1, we enter into this folder and we select it. So now the system is going to automatically submit the simulation. So I can now enter the Cloud HPC and wait for this process to be actually submitted. So I'll just wait for the system to generate the input files and submit it on the Cloud HPC platform. This is going to automatically generate the mesh on the cloud, and once that is generated, we can download the files. You see, automatically the new simulation where the mesh is going to be generated is opened, and this is going to take probably 10 minutes to the system to actually generate the mesh. I let the system compute the mesh because once that is completed, I want to download the results. In the meantime, we carry on with the presentation. We're going to talk about future steps and future events we're going to hold, and in the meantime the system processes this mesh. So I'm going to proceed with this presentation. Hold on. Yeah. So yeah, the Cloud HPC BC Snappy has not been released officially yet. So what you have seen is a preview of what our mesh tool is going to look like. The official release is going to be during the ASME Turbo Expo, which is an event held in London at the Excel Exhibition Center in London, where we're going to be an official exhibitor. So we have a stand dedicated to Cloud HPC, to BC Snappy, and to several other tools we're going to present in that specific event. So you're all invited to come and visit us at that specific event. You can email us. You have here the email address of the company in order to get free ticket to attend the event. The Turbo Expo 2024 in London is not just the only event where we're gonna attend, where we're gonna be exposing, but we are also exposing into two NAFEMS events. The first one is going to be in Italy at the beginning of May 2024 in the city of Siena. And the second is another event held in United Kingdom in the Staffordshire region, and is going to be the NAFEMS UK conference around mid of June, 11 and 12 June 2024. If you need any information about all these events, you can feel free to email us in order to get tickets, get information about tickets, or maybe book a meeting with ourselves and know the news we can propose to you during these events. Well, I also invite you to register to the cloudhpc.cloud website in order to also take advantage of the cloud technology and also to experiment how you can handle really huge mesh on the cloud thanks to the Cloud HPC technology. In fact, the advantages of performing the mesh not on my local PC but remotely on the cloud is the fact that if the mesh size becomes really big, like 100 million cells, well, in that case, everything can be performed with a dedicated hardware resources, which is huge in terms of CPU power, in terms of RAM requirements. So it's really a professional service dedicated to computing power. So before saying see you later, we can see what's happening over here. Well, if you see in the first Cloud HPC BC Snappy, what happened is that the system actually was able to set up a case, and once this case is completely defined, the snappy mesh is defined and is placed in run. So I can now enter the snappy tool where actually the mesh is going to be processed. So the mesh is going to be generated into two steps. The first one is the setup of the mesh, and the second one is the mesh generation using, in this case, snappyHexMesh of OpenFOAM 10. Okay, we are compatible with several versions of Snappy from the two main OpenFOAM branches. So the openfoam.com and the openfoam.org from the OpenFOAM Foundation and OpenCFD. It is possible also to submit the simulation using cfMesh, and now that the simulation has started, I also have access to the remote desktop here at the bottom. If you see, I just had to refresh the window, and this is the remote desktop where I can actually see what is happening on the Cloud HPC, and I can, I can open ParaView and see the mesh and monitor the mesh as it is computed at runtime. So in here you see automatically all the features and all the steps that has to be computed with Snappy are performed by the system in a complete automatic way. I didn't have to do anything in particular. I can just interact if I want with the remote desktop, just to open the mesh or to do anything I want with the Cloud HPC, okay? But I don't need to take care of my mesh generation because that is performed on the Cloud HPC in an automatic and independent way. So now we just wait for Snappy to finish. In the meantime, we can monitor. We just double click on tail log down here, and here it is. We have a log produced by Snappy at real runtime, so we can actually see what if we can read this log. Well, an explanation of what is happening in this log can be performed. Sorry, it's beyond the purpose of this webinar. So I invite you to get in touch with me and via email independently, or to get information, let's say separately, about this log using the user guide or using any other information. Well, eventually, when the mesh is completed, okay, the system is going to upload the mesh on the Cloud HPC, and I can assess it separately, and I can actually handle this mesh, download this mesh on my computer by simply clicking download button over here. With this webinar is completed. As I said, I invite you once again to register to the Cloud HPC and to email us if you need further information, and to stay in touch with us using the social in order to get more updates. See you later.